So are you ready to start, João?
Yes.
Okay. So I will just shut my microphone now and let you up with your presentation. I will also shut down my video so that we can have the more internet access to your presentation, video, and speech. So it's up to you to start.
Okay. So thank you very much, Emmanuel. Many thanks for your kind introduction and for setting up this webinar. This talk about the fire behavior of pultruded GFRP materials and structures, it will last, I would say, around 35 minutes, more or less. The main goal here is to present a review in this field where we did some work in the past. And also to highlight our contributions in this field. So this is the outline of my presentation. So I will start with a brief overview of research activities on FRP composites at IST, University of Lisbon. And next, for the talk or the webinar itself, I will address first the GFRP material properties at elevated temperature, the fire reaction behavior of the material, the fire resistance behavior of GFRP members, and finally some concluding remarks. First, let me present my university, IST, the School of Engineering of Lisbon University. It was founded in 1911. We have about 11,000 students, several master and PhD programs, about 1,000 faculty members, and we are organized in 8 departments. Mine is civil engineering. So this is, by the way, my research group. It was started in 2008, and it is presently formed by 5 postdoc researchers, 8 PhD students, and each year we host around 6 master students. So in terms of research subjects, this slide shows some of the topics that have been relevant for different types of FRP components. So profiles, sandwich panels, reinforcing bars, and strengthening systems. I highlighted in red those where we already gave some contributions in the past, and in blue the ones where we started to work more recently. So you can see that most of our expertise is concerned with pultruded profiles and sandwich panels. So it was only more recently that we started investigating reinforcing bars and strengthening systems, especially regarding their fire behavior, which is, by the way, the topic of this presentation for the pultruded profiles. So before going into that, I will just show you an overview of some of the studies we did here in these different topics. This will be quite fast. So for FRP profiles and regarding the material and structural behavior, I would highlight the experimental and numerical investigations we did about the buckling behavior, either local or global, of columns and beams, and more recently a relevant topic which is concerned with the web crippling phenomenon of the webs and damage progression in this material. We also developed GFRP concrete hybrid systems, so aiming at taking full advantage of both materials, using concrete to increase stiffness and prevent instability phenomena. Here you can see some of the experiments we did. So for connection technology, with EPFL, we investigated the behavior of adhesively bonded connections. And more recently, we also started to work on bolted connections. So it's an old topic, but now we are focusing on damage progression, which is more recent, and also on the development of connecting parts that somehow allow overcoming some of the limitations of the GFRP material. We are also investigating the dynamic and seismic behavior of GFRP frames, comprising these new connection systems. and analyzing also the effects of partition walls, in this case made of sandwich panels, and the seismic behavior of three-dimensional frames. This is a video I would like to show you of shaking table tests we did at IST. This is not possible with this webinar system, but I leave you the link of this video, and you can have a look at it at the end. So durability is also a very relevant topic for us. Here we are completing a comprehensive study on the durability of FRP profiles made of different resins and bonded joints with different adhesives after exposure to different aging conditions, both accelerated and natural. Then for sandwich panels, which is also a relevant topic for us, we focus on shape and material optimization, and also on the connection technology, which is illustrated in this slide. At the panel-to-panel level that you can see here, and also at the panel-to-wall connection system, namely for rehabilitation solutions. Another relevant topic is concerned with creep of sandwich panels and of their constituent materials. In this case, polyurethane foam and GFRP skins that we tested in shear and bending at different load levels and at different temperatures. For GFRP bars, this is a recent topic, as I mentioned. We are starting to study the fire behavior of this type of reinforcement in concrete members. So we are addressing the bond behavior at elevated temperature and also the fire behavior of concrete slabs with this type of reinforcement. Concerned with this topic, but now for FRP strengthening, we completed a quite comprehensive study on the bond behavior at elevated temperature, so both for EVR and NSM systems, and the fire behavior of CFRP systems when used with concrete elements, where we try to develop tailored fire protection systems, namely at the anchorage zones. I should say that some of these ideas that we used here, they stem from the knowledge we got from the study of pultruded members that I will show later. I should also say that we try to have a strong collaboration with the industry in the development of applied projects. Here you can see the Click House project, where we developed a prototype of an all GFRP emergency house with all facilities and building services included. So this is the first prototype that was built within this project. We also designed the first hybrid footbridge in Portugal with steel girders and a multicellular GFRP deck panel with snap fit connections. You can see here the completed footbridge. And finally, the Pontalumis project that we developed in collaboration with the Portuguese company, ALT, and the Minho University. So this is also a hybrid concept, but here we use GFRP pultruded girders and a very thin deck made of steel fiber reinforced concrete. So there is no conventional reinforcement in this footbridge, which was also very recently installed in the north of Portugal. You can see here the completed project. So after this introduction about our activity at IST in this field of fiber reinforced composites, I will start the overview about the fire behavior of pultruded GFRP structures, which, as you know, is a concern for civil engineering, especially for buildings. And it's a field where there are lots of aspects that we do not understand yet in full depth. So I will address three main aspects: the GFRP material properties at high temperature, next the fire reaction behavior of GFRP profiles, and finally the fire resistance of GFRP structural members. So starting with the GFRP material properties at elevated temperature, we need to go to the degradation mechanisms at elevated temperature. And as you may know, high temperature affects especially the polymer matrix. So for temperatures between 100 to 200 degrees, this depends on the type of matrix we use, the material changes from a glassy state to a viscous or rubbery state in a process called glass transition. So this process, it can be assessed in different ways. One of the most common are DMA tests, which provide, you see here the outputs, the change with temperature of 3 parameters, the storage and loss moduli, and the tangent of delta. And any of them provide an estimate of the glass transition temperature, or TG. The second mechanism, and you will see next the effect that this process has on the material properties. So the second mechanism, it occurs for higher temperatures, somewhere between 300, 600 degrees. And for that, we have the decomposition of the polymer matrix. So in the presence of oxygen, the volatile gases that are formed, they ignite and they result in toxic gases, smoke, and heat. And finally, for temperatures around 1000 degrees, the glass fibers, they soften and melt. And therefore, as a consequence, there are a set of heat-induced damage mechanisms in the material. So this is the original section, and after burn-off, we will have char formation, matrix cracking, applied lamination, and eventually ablation with layers of material falling away. So in addition to the release of heat, smoke, and toxic gases, there are also changes in the thermophysical and mechanical properties of the material. So for the thermophysical properties, temperature, first of all, will cause a reduction of the density. You can see it here in this plot. These are results of TGA tests. So the density decreasing with the temperature increase. Also the effective specific heat, which is this red curve in normalized values in this plot, which is quite low at ambient temperature, and this is good because the material is insulating, it shows the insulation capacity of the material. So it first presents a peak, okay? It increases significantly during the decomposition because this process is very endothermic, and then it decreases after this process. So for thermal conductivity, you can see actually this was the property I was mentioning that is very low. So this is the one that reflects thermal insulation capacity, not the specific heat. So you can see that it initially presents a reduction here with the decomposition of the matrix. So this is basically due to the fact that you have delamination and pore formation in the material, and this helps insulating. And then it progressively increases due to the increase of the fiber volumetric fraction. Now, for the mechanical properties, so we have the degradation of the constituent materials, the fibers and the matrix, and also of the composite action at the fibers matrix interface. And consequently, we will have a reduction of the stiffness and strength properties of the materials. And as you can see in this picture here, the reductions, they typically follow a sigmoidal pattern. And at the same time, we'll also have changes in the failure modes. So it is more likely that at elevated temperature, we have shear failure at the fibers matrix interface, and also, as you can see here in these two figures, fibers buckling or kinking under compression. So in this specific topic at IST, we performed a set of mechanical tests in pultruded GFRP material in tension, shear, and compression from ambient temperature up to 250 degrees. You can see the setups in these pictures. So the procedure was quite simple. So we used laminates or I-section segments for compression. We first heated the material to the target temperature and then loaded the material to failure. In shear, I should say that we used two different setups. The one that you see here, which are 10 degrees off-axis tests, and the one that is shown here, I went too fast, I'm sorry, which is the Iossi-Pesco method. Let's look at the results. These figures, they show the mechanical properties as a function of temperature, normalized to room temperature, obtained in this study and also by other colleagues. So I would highlight, first of all, for the tensile properties, which are shown in blue, and as you may know, these properties, they are fiber dominated. So tensile properties are the least affected for this reason, especially the modulus, which suffers very little reduction for this temperature range. On the other hand, the tensile strength, which is shown here, it is more affected than the modulus because the resin is no longer able to distribute evenly the stresses among the fibers. Now, compressive strength, which you see in green, and the shear properties that you see here in red, so both the shear strength and the shear modulus, they are all resin dominated, and you can see that consequently they experience much higher reductions with temperature, becoming almost negligible at the end of the glass transition process. For the shear strength, I would also like to mention the significant differences we obtained from 10 degrees off-axis tests and the Iossi-Pesco setup. So here you see that the setup we use has a big influence because for 10 degrees off-axis tests, we have influence of the tensile stresses in the fibers. So after looking at the material properties, let's now review the fire reaction behavior of the material. So first of all, and I think you know what fire reaction means, these are basically the properties that describe the potential fire hazard of construction materials, namely their contribution to fire growth and to human survivability. These properties, they can be assessed based on several tests, and the two that are among the most relevant are the cone colorimeter test and the SBI test, which is presently the basis of the European regulation in this field. So for unprotected GFRP material, and we will then see what happens when we use protections, there is plenty of literature from different industries, and previous results, they basically show that the fire reaction behavior is not good, and it depends on several parameters, namely the type of resin, the fiber content, the laminate thickness, the incident heat flux, and local conditions. So this left picture here, it shows the time to ignition for different resin systems as a function of the heat flux. You can see that the ignition times, they are quite low, so this shows the flammability of current resins. And you can also see the much better performance of phenolic resins, so these gray dots. This better performance is also reflected in the right plot, the flame spread distance as a function of time, which is 0 in phenolics. In terms of toxic gases, so this table here above, you can see that the different resins, they release high quantities of CO and CO2, and for vinyl ester, which together with polyester, they are among the most used resins in FRP profiles, you see that there are no traces of highly toxic gases, as reported by these colleagues, Moritz and Gibson. while for epoxy and phenolic, you see some traces of these two gases. At IST, we did some tests in a cone colorimeter on glass polyester laminates under different heat flux, which I show here to illustrate the fire reaction behavior and how different properties change with time. So in the top pictures, you see different stages of the test, and in the bottom, you can see different fire reaction parameters as a function of time. So in this first stage, there are no signs of degradation. So the mass remains more or less constant, and you see no heat, smoke, or toxic gases, CO2 or CO, being released. Then, in a second stage, when the surface temperature attains a critical value, ignition occurs, the heat release rate increases almost simultaneously, as well as the release of smoke and toxic gases. And at this stage, you see that the remaining mass starts to reduce at a very high rate. In a third stage, when the remaining resin is reduced, the flames start to die down, and the release of heat, smoke, and CO2, they all decrease. Finally, in a fourth and final stage, after all resin is decomposed, you see no further signs of thermal decomposition in terms of heat, smoke, and CO2. Now, to improve this poor fire reaction performance of GFRP, two basic approaches have been followed in different industries. The first has to do with the use of flame retardants, which can be added to the base resin and eventually react with it, and the use of inherently flame retardant resins, that is, phenolics. So both approaches, they significantly improve the fire reaction performance of the material. However, they may affect the mechanical and durability properties, and more importantly, for structural applications, they generally do not improve the mechanical performance of the material at high temperature. And therefore, although being effective in terms of fire reaction, they are not really helpful in fulfilling fire resistance requirements. So we may need to seek an alternative approach consisting of using protective layers, either coatings or thick boards. So using this alternative approach, we did a set of new tests in the cone colorimeter in GFRP laminates protected with three systems: calcium silicate boards, lightweight mortar, and an intumescent coating. And in these tests, since we are basically testing the protection materials, no signs of combustion were observed during the 30 minutes of testing. And therefore, as you can see in these two figures, the previous fire reaction properties I showed before, their average values that you see in the left picture and the maximum values that you see in the right picture, they were all very significantly reduced, especially for the thicker protections with mortar and with boards. So, as a summary, this table shows the European classes of fire reaction for the different fire protection systems that we analyzed in our study. In the second column, the classes estimated from the cone tests using a software based on a flame spread model, and in the third column, obtained directly from the SBI tests. So basically, you can see that without passive protections, the GFRP material is somewhere between classes C to D, which involves some restrictions in terms of building applications, especially in evacuation routes. And with any of the protections, you can see that the performance is substantially improved with classes from B to A, and therefore with much less end-use restrictions. So now let's discuss a different topic, but as you already saw, pretty much connected to the former one of fire reaction, which is the fire resistance behavior. So first of all, let me remind what is fire resistance. This is not a material property. It's the period of time during which an element, either structural or non-structural, maintains three different functions: load-bearing capacity in case of structural elements, no collapse or excessive deformations under load, its integrity against flames or gases, and the insulation of the cold phase. So regulation in buildings basically establishes periods of time for different types of elements. So in the next slides, I will describe results obtained from furnace tests or fire resistance tests on slabs, beams, and columns, and at the end, the corresponding modeling of these experiments. So at IST, we did a quite comprehensive experimental program on the fire resistance of tubular beams. They were tested under 4-point bending, and they were exposed to the ISO 834 curve, which is a standard fire curve. Here you can see the setup. So this is the furnace we used. The beams were placed on top of the furnace, and they were loaded with 2 water containers, which is a quite convenient system because you know that the load will be kept similar during the test. In terms of parameters, we tested different passive protections as panels or as an intumescent paint or mat. And we also checked water cooling, which had been successfully tested at EPFL a few years before. We also evaluated the number of sides exposed to fire, either 1, so only the bottom surface, so as a slab, or 3, the bottom and also the sides, so more similar to a beam. And also we tested 2 different load levels expressed in terms of mid-span deflection in terms of mid-span deflection levels. So for the thermal responses, just highlights of some of the results we obtained. You can see here the temperatures for different beams under one side exposure. So for the unprotected beam in the left, you can see that the center of the bottom flange, the red curve, it attained the decomposition temperature only 10 minutes after the test started, and that the top flange, it reached the TG at collapse. With calcium silicate protection, as expected, temperatures considerably decreased in all section walls, and with water cooling, temperatures in the webs and top flange, they were kept below the TG for the 2 hours of testing. Now for 3-side exposure, you can see here the influence of changing the type of exposure in the temperatures for both unprotected and protected beams. So as expected, for 3-side exposure, which are the dashed curves in this plot, compared to 1-side exposure, the continuous curves, you can see that there was a considerable temperature increase in the top flange in blue, and especially in the webs in green that were now directly exposed to heat. So in terms of mechanical response, we can see here in this slide a picture with mid-span deflection increase as a function of time for the different beams. I will help you out with the different curves. So in red, for 1-side exposure, we can see that the unprotected beam suffered a rapid deformation increase. This was due to the temperature rise and the consequent loss of stiffness, first in the bottom flange and then progressively in the webs and top flange. Next, for the passive protections, you can see that they had an effect in slowing down the deformation increase, especially for the thicker protections. And for the water cooling, this blue curve, you can see that they followed pretty much the temperature. So there was an initial increase due to the loss of stiffness of the bottom flange and the heating. And then the deformations almost stabilized at some point, so indicating the efficacy of this system for this type of exposure. In the right plot, you can see for an unprotected and calcium silicate protected beams, the influence first of three-side exposure. So there was a much faster mid-span deflection increase and failure, and also the effect of increasing the load level in the fastening of the mid-span deflection increase. So in this plot, again, this was a video that I would like to show you. So it's the test of an unprotected beam under one-side exposure. So you can just click in this link or type it at the end of this session and see how this beam failed or how its behavior during this fire resistance test. I will show you then just the failure modes, which for the different beams, they were basically two types. One that you see in these two pictures, flexural compression of the top flange. You can see here a detail of the kinking failure of the top flange. And the second type, which was due to shear and transverse compression of the webs and top flange under the applied load, so that you can see here. Okay, so basically we did not have a tensile failure of the bottom flange, although temperatures at this wall were much higher than those at the webs and top flange. And of course this is explained by the much higher residual tensile strength, and also due to the fact that the anchorages of the bottom part of the fibers were kept at ambient temperature, and of course this helped in this failure modes. Now, just a summary of the fire resistance of the different elements in bending. So first of all, for the unprotected beam under one side exposure, so this one, so you can see that the fire resistance was just a few minutes more than 30, okay? And you can see that the performance was much worse than multicellular panels that had been tested at EPFL, which resisted almost 1 hour. But I must say that these panels, they were much higher, okay, about 20 centimeters instead of 10. And their wall thickness was also much bigger. Next point I would like to remark is that all passive protections were effective, granting fire resistances higher than 60 minutes for one side exposure, and therefore offering in this case a much simpler and economic alternative to water cooling. But it's relevant to see how the performance was drastically affected with the three-side exposure. So in this case, even with passive protection, we did not get to the 60 minutes of fire resistance. And these results, they are consistent with the very low fire resistance that had been reported by Ludwig. These are tests conducted at EMPA in I-section beams, but exposed to fire in four sides. And finally, and as expected, the influence of the increased load, which caused the moderate, I would say, reduction of the fire resistance. Okay, now let's look at columns. So we performed, in this case, similar tests, so in similar tubular profiles, but now under axial compression. So the setup that you see here is pretty much similar to that used in the beams, except that we now used a hydraulic jack to apply the load. As protection, we assessed again different fire protection systems, water cooling, now with full section, okay, so the entire cavity filled with water, either standing or flowing, and again calcium silicate boards because they had performed quite well with the beams. As for the previous experiments, we also assessed the number of sides exposed to fire, 1 or 3, and the load level as a function of the actual shortening as a function of the column height. So height divided by 750 or 1500. So for the thermal responses, you can see here the results for one side fire exposure. So for unprotected columns here at your top left and with calcium silicate protection, the results were pretty much comparable to those obtained for the beams. For water cooling in the bottom, either standing or flowing, as expected, it conferred very effective thermal protection, especially with the flowing water. And with this, we were able to keep the top flange and almost the entire web below TG for 2 hours. So in terms of mechanical response, which is quite more complex than that for beams, this picture shows first the variation of the actual shortening as a function of time for the different columns. In some cases, there was a slight initial actual extension due to the thermal expansion effect, and this was then progressively succeeded by an actual shortening of the material due to the stiffness reduction caused by heating and, of course, due to creep of the material. In terms of lateral deflections, so out-of-plane deflections, the columns first presented inner lateral deformations. This was basically due to the thermal gradient installed in the section, and then they progressively presented outer lateral deformations due to two reasons. First, the differential stiffness reduction, which was much bigger in the bottom part of the section, and also due to the eccentricity of the applied load, whose position was kept constant during the test with respect to the stiffness center of the section. So here again, this was a video that I would like to show you. So if you want, you can see it later in this link. So it's a test of an unprotected column under one side exposure. So I will run to the failure mode. So this would be the end of the test. So collapse caused always due to the crushing of the hottest walls. So the bottom flange for one side exposure that you see here in the top, and also the webs that you see here in the middle for three side exposure, which was followed by the failure of the remaining walls. So here you can see a summary of the fire resistance of the different columns tested in this study, and also comparison with results obtained elsewhere. So first, I would highlight the much lower fire resistance of the columns compared to equivalent beams, if this comparison can be made. This is basically explained by the lower residual strength of the material in compression. For unprotected column under one side exposure, so this one, the resistance now was only 15 minutes, which is very low. Again, lower than the resistance of the multicellular panels that were tested at EPFL, as I mentioned, with higher height and wall thickness, that reached about 50 minutes of fire resistance. So passive protection, in spite of its efficacy, we could not get to the 60 minutes, even for one side exposure. And you can see that for three side exposure, the performance was again drastically reduced, especially for water cooling, either standing or flowing. And as for the beams, and as expected, load level also influenced the fire resistance of the columns. So now about the modeling of the fire resistance behavior. So this is a quite complex issue, so I will try to keep it as simple as possible, or to give you an overview of the work that has been done in this field. So in general, most colleagues have been following an uncoupled approach in which the thermal response has been modeled first and then the structural response. So the first step basically comprises applying the heat transfer theory, considering different aspects, the temperature dependence of thermophysical properties, the endothermic decomposition of the resin, char formation, mass transfer, different degradation mechanisms. So previous works in this field have very different levels of complexity, but one aspect that is transverse to all of them is that they in general consider quite simple boundary conditions or geometries, generally laminates or very simplified cross-sections. For the structural responses, different approaches have been pursued depending on the geometry of the problem. And again, different features were incorporated in the models, namely the temperature dependence of mechanical properties, the effects of geometrical nonlinearities, and the effects of thermal deformations and creep. In this case, I would point out as main limitations the uncertainty about several material properties which are not yet determined in the literature, and the applicable failure criteria. Let me show you work that was done at IST within the thesis of Cristina Lopez. In this work, we tried to simulate the fire resistance tests of GFRP beams and columns. We followed a two-step procedure, as in previous works. First, we did 2D numerical simulation of the thermal response of the section, and the main innovation here was the consideration of the heat exchanges in the cavities of the walls due to the radiation between the walls and the flow of the air enclosed in the cavity, which for some cases proved to be quite relevant. For this, we had to use a CFD code with our thermal model. Then, as for other studies, we use these thermal responses as input in a geometrically nonlinear beam model. So here you can see two outputs as an example. At your left-hand side, you can see the resultant velocity field after 1000 seconds. You can see here the formation of the Bénard cell, so the convection of the air inside the cavity, which had some influence in the temperature distributions. And at your right-hand side, the temperatures in both the material, the solid material, and the fluid. In your bottom left picture, you can see comparison between experimental and numerical temperatures. In red at the center of the bottom flange, and in blue at the center of the top flange. So here the main point is that the cavity heat exchanges are very relevant. So for instance, if you do not take them into account, the bottom flange, it basically does not heat in the numerical model. So by incorporating these effects, we obtained a much better agreement with the experimental data. At your right-hand side, you can see an example of the midspan deflection increase for one of the beams as a function of time. Again, the comparison between the test in red and the model in blue, so without failure criteria, I should note. But given the complexity of the phenomena involved and all the uncertainties at stake, I would say that the agreement is quite reasonable. And now we are getting to the concluding remarks. So I would say to sum up that there are well-founded concerns and still several uncertainties, I would say many uncertainties about the fire performance of GFRP profiles. These are delaying their widespread acceptance, especially in buildings. So the fire reaction performance of the material is poor, but as I showed, it can be easily improved. The most important challenge consists of keeping the structural integrity for sufficiently long period of time. And in this respect, phenolics and flame retardants are not really effective solutions. And the limiting criterion for fire resistance is really approaching or exceeding the resin in structural parts under compression and or shear, and not that much in tension. And for that reason, fire resistance depends significantly on the type of loading. It is either bending or compression, the cross-sectional shape, if it is open or cellular, and wall thickness, the number of exposed surfaces, so the building architecture here plays a very important role, and the type of fire protection. And therefore, depending on these factors, the fire resistance can vary from only a short minutes to more than 2 hours. As I mentioned, there are many research needs in this field. I listed here a few. Several material properties at high temperature, they need to be determined, both physical properties and mechanical properties. Also, the influence of creep at elevated temperature. There are still many things that we do not know yet. The behavior of connections. So I just mentioned here results of tests in individual members. So we need to know how connections behave both bolted and bonded. Also, the post-fire behavior and repairability of GFRP members. And finally, the design guidance. I did not mention this, but existing documents in different countries, they basically provide no guidance, okay, for fire design, because we simply do not have enough information yet to include such information in this type of documents. And with this, I would conclude this webinar. I would like to thank again Emmanuel Ferrier and for setting up this webinar. The work I showed here was done mostly in collaboration with several colleagues, students, postdoc researchers, and also with industrial partners. So many thanks to them as well. And please feel free to contact me for any further information, even after the short discussion that we will have later. So if you remember any questions, please contact us, okay?
So thank you very much for this very nice talk, very impressive about all the works you have done. So if any of the participants have any questions, you are free to ask them. I can open your microphone, or you just have to, maybe can ask the question in the public area, chat area can be used to ask the questions. Maybe I have one to open the discussion. You mentioned the fact that the research should be done also in the field of the connection problem. If we look to other structural components such as steel or even wood, most of the time this part is quite sensitive for the design. What is your experience in this field? Do you have already some results, or have you seen some coming from the literature about connection between FRP system?
Yeah, many thanks, Manuel. This is, well, we did not do work in this field yet. I'm not sure that there is much work in this field done so far. I listed here, I mentioned here recent work I saw and I read from these colleagues, Yubai and Toby Mottram and their student. I think this is one of the first works in civil engineering on connections. And I'm pretty sure that the connections will be as sensitive or even more sensitive than the members. I recall, for instance, with bolted connections, we have generally problems of crushing, so bearing, so compression, and problems of shear out. So these are two types of failure modes that are resin dependent, or are pretty much resin dependent. So I'm sure that with elevated temperature, the problems will increase. So I would say that this is the next step, but we also have several doubts still on individual members. So connections is definitely an important topic, but individual members are also yet to be understood. Okay.
Okay. And at the end, if we see all the work you have done in this area, what we could conclude is that, in fact, is not more complex than steel problem. Maybe the behavior is a little bit less efficient, but it's quite comparable to the one we can have with steel. Is that a good conclusion, or you think that we'll have more problem with GFRP than steel? Because if we see all the curves of properties you mentioned, between 200 and 300 Celsius degrees, generally where steel have a lot of drop in properties, and it seems that for GFRP it's very similar. So do you think that it's more or less comparable for steel guider for the design? Or?
Yeah, this is also we in this field we always try to compare with our competitors or the competitor materials. These comparisons are not very easy, but what I can say is that with steel, the critical temperature, if we do have a critical temperature in GFRP, which is also a point here, because as I showed, the reductions in material properties, they are very different depending on the stress state. So for tension, we have a very good or a much lower strength decrease and stiffness decrease compared to compression and shear, for which we have very big reductions in properties for quite low temperatures. And so if we think of a critical temperature for GFRP, it is much lower than for steel from one point. But from another point, the temperature rise is much faster in steel because steel has a much higher thermal conductivity. Okay. So I would say that both materials, they need to be protected, okay, in buildings. And we do this with steel without any problem. So all these, the civil engineers or designers, they know they have to protect steel, okay? So I think we need to follow a similar approach with GFRP.
Okay. Is there any question from colleagues or students? Okay, so, well, maybe we can stop here. I will just send you again my email for those who would like to get the link for the YouTube channel so that you can just send me an email to get the link. It will be easier. Or the link is already available on the IIFC website. I will put this webinar. It needs some time to record everything, so maybe in 1-2 days. So thanks again for your very nice presentation, very efficient, and I think we have a clear overview about the problem. And see you in very soon in another event. Thanks again, and bye everybody.
Bye.
Bye. Thanks.